Hello students, today we are going to do a little virtual lab just with on the board, but I'm also going to be actually doing a little lab here on this video as well. Before we jump into the lab, I hope that you had a chance to watch the thermal energy transfer video. I think that's what I called it. That will really help you understand the type of math and calculations that we're going to be doing in this lab. So if you could please watch that video first before you attempt to do this lab. All right, and then in addition, before I actually explain what we're doing in the lab, which I'll kind of draw on the board, I did have one concept that I thought would be useful for us to discuss beforehand. And this is something that many of you probably already know and maybe haven't thought about it, but you probably actually already know what I'm about to talk about here. So if we could just envision a pot of water on the stove. Say the water is at 25 degrees Celsius, which is about room temperature. So let's just pretend that it's room temperature water. And just for the sake of your understanding, just picture that you put it on your stove and you turn on the stove. Well, understanding that when you turn on the stove, that heat is being transferred from the stove into the water sample. Okay, what I want to talk about here is what's actually happening energetically, what kind of interactions are happening with those water molecules during the course of that process as you're heating it up. So in order to do this, and we'll use this in the lab, one of the things that's really helpful for chemists is to draw what's called a heating curve. And a heating curve is just like a y and x axis that pretty much always looks the same. On the y-axis you have temperature, usually in degrees C, and on the x-axis you have, I usually just see heat added, okay? It's actually can also be time, because as time is passing, you're adding more heat, but usually I see heat added. And let's just talk about what's happening to our sample, okay? I'm not going to draw a full heating curve for water, which goes from ice all the way to steam, but I just want to talk about this sample here. So let's just start at 25 degrees C. I'll just put that temperature on our y-axis. So at the beginning, before I turn my stove on, I'm at this point on our graph. So I have not added any heat, okay, and I'm at 25 degrees C. When you turn that oven on or the stove on, you are adding heat. So our line is going to have to move from left to right here. And during this phase, if it's at 25 degrees, during the first phase of this process, this line is going to look like this, a diagonal line. And let's talk about why. As you add heat into your 25 degrees C water, okay, as you're moving left to right, you're adding heat, your temperature is going to rise, okay? Just common sense, we know that. The temperature is going to rise. Now, it's going to continue to rise up until it hits its boiling point, which is 100 degrees C. We know that from that's a known value. So your temperature is going to keep rising until you hit 100 degrees C, that point called the boiling point. During this part of the curve, the law or the equation that governs that temperature change is Q equals M times CS times delta T. During any of these diagonal phases of the curve, the amount of temperature change is going to be completely related to the amount of heat that is added, and through also including how much mass is present in your sample, as well as the specific heat capacity. So that equation or that law governs how much your temperature will change. But when you hit 100 degrees C, as this temperature rises to 100 degrees C, something different happens here. And we know that what starts to happen is that the sample will begin to boil, which really means that it's vaporizing under the surface. Okay, so you're getting little gas bubbles under the surface, and of course they will rise and then bubble away, and that's gonna start to boil. Okay, at that point, something changes in the sample. During this diagonal phase, all of the heat, let me write all of the added heat just goes to or goes towards increasing temperature or increasing the kinetic energy of the water molecules. At this phase, they're just speeding up faster. But when you hit 100 degrees C, you no longer are going to have an increase in the temperature. You are actually going to flatline your temperature. You're still adding heat, but your temperature will no longer rise during that phase. As soon as you hit the boiling point, your temperature no longer increases. And a lot of people know that a boiling pot of water is 100 degrees C. It doesn't just keep, as it's boiling, it doesn't keep increasing in temperature. So why does it flatline its temperature? The reason is that during this phase, all of the added heat goes to something different. Goes to really to breaking what are called intermolecular forces. Okay, these are something that we'll study at the very end of the semester, but intermolecular forces are essentially the forces that hold the liquid together. So the heat is no longer being put towards temperature changes, it's being put towards taking a liquid, which has the molecules fairly condensed, and breaking those forces that are keeping it together so that you can vaporize, so that you can become a gas. And so the key here is that something different happens as soon as you hit this boiling point. Now, just as this section of the curve has an equation that governs it, so does this section of the curve. Whenever you're undergoing a phase change, like in this part of the curve, it's a liquid going to a gas. It's a different equation, and the equation is Q equals, in this case, delta H of vaporization times the number of moles. Okay, we're not going to talk too much about delta H of vaporization, but it's a constant and you can look it up. But it basically tells you how much heat is required per mole to turn something from a liquid to a gas. And that's really going to be a different part of the curve or a different kind of governing equation than this one. This one doesn't involve any temperature changes because there is no temperature changes during the process of boiling. So I just wanted to make that point because that's going to end up affecting how we understand our lab, is that during a phase change, you don't get rises in temperature. All the added heat actually just goes to changing the phase, to breaking those intermolecular forces that hold that phase together. All right, so that's just kind of a principle. It's actually something that's covered in chapter 11, but I needed to fast forward a little bit to it to understand this lab. Okay, so what are we doing in today's lab? This lab is something I literally just kind of invented and thought of. I mean, I'm sure I didn't invent it, but I thought of it myself. It's something that I can do with the stuff in my house. I just made a whole bunch of calculations on a piece of paper. I believe it's correct, and so I'll just kind of teach you kind of what I was thinking about here. In the lab today, we are going to take a sample of hot water. I'm going to have it in a measuring cup. This doesn't really look like a measuring cup, but anyhow, I'm going to have it in a measuring cup, and it's going to be hot water. Now, I don't know how hot exactly it's going to be. We'll go ahead and measure it in a little while, but it's still on the stove getting hot, being watched by my children. So for now, just for the sake of the explanation, let's just say it's going to be below boiling temperature. Let's just call it 95 degrees C, so hot water. And what I want to do is just drop an ice cube into the water, okay? So I made some ice cubes. Ice cubes are rectangles. And the ice cube, we're going to put it into the water. And everybody will know that the ice cube will melt because we're putting it into hot water. And essentially the question I'm going to ask is, can we calculate or can we predict the final temperature of that water? You know, regular people just put ice cubes into hot water or whatever, and they just see it gets warmer. Or sorry, like cooler, I guess you could say cooler. We're not regular people. We're going to calculate it using the laws of chemistry. It actually can be calculated, and then we'll do the experiment, and then we will see how close we were. That's really what the lab is going to be. Okay, hot water. Now, let's talk about the ice cube. The ice cube, my refrigerator, I read on my refrigerator that it says that my freezer is 0 degrees Fahrenheit. Now, with all of our constants, we need Celsius. So I haven't done a lot of Fahrenheit to Celsius with you guys, but we need to put this into Celsius. So essentially, the equation for Celsius, you can just do this along with me, is simply the degrees Fahrenheit minus 32 divided by 1.8. So let's go ahead and figure out how cold my ice cube is. If it was 0 degrees Fahrenheit, because it's in a 0 degrees Fahrenheit freezer, it's going to be the same temperature. So we're going to put in a 0 here. So 0 minus 32, negative 32 obviously, divided by 1.8. So I'm getting negative 17. Let's just do one decimal place here. Negative 17.8 degrees C. That is how cold my ice cube is going to be. And by the way, this lab has lots of assumptions, lots of places where there's error, which is something I'll probably ask you about at the end to make a couple comments on, because I'm doing it in my house with a bunch of rudimentary tools and things like that. So that's kind of something we have to consider. Anyhow, that's how cold my ice cube is. Now, once I drop it into the hot water, what is the direction of the heat flow? Is it going to go from the water into the ice or from the ice into the water? And hopefully by now we know heat always flows from hotter temperature substances to lower temperature substances. So the heat is going to flow from the water into the ice. Now, this is where that thermal energy transfer video is really helpful, because I kind of explained this next step. In order to calculate, because what we're trying to do is figure out what is the final temperature of the water, we are going to understand that these two substances, the hot water and the ice, are going to you're going to keep transferring heat from the hot one to the cold one until you reach what's basically called thermal equilibrium, which is essentially they're at the same temperature. There is going to be a final temperature to the whole system, and that's when the heat transfer is going to stop. You're going to keep transferring heat until they're the same temperature. So really, at that point, when they're at the exact same temperature, when this substance and this substance are at the same temperature as each other, it is true that whatever amount of heat that is lost by the water, so this is our governing equation, whatever heat that is lost by the water is going to have to equal whatever amount of heat is gained or picked up by the ice. And this is our kind of governing equation. Because of the law of the conservation of energy, this heat transfer is going to happen, but he's going to lose as much as he's going to gain, and then they're going to result in the same temperature as each other eventually. So they're going to leave this equation up the entire time. Now, this side of the equation is pretty easy. We are just going to substitute in, let me kind of draw this down here. We are just going to substitute in, let me rewrite that. Because this water is just going to be dropping its temperature. We're just going to substitute in, instead of Q, we're going to substitute in mass times specific heat capacity times delta T, which is T final minus T initial. T initial being 95. All right, so that's going to be that side of the equation. That's what's going to happen with this water. His temperature is just going to keep dropping. That's all that's really going on with him. His temperature is just going to keep dropping as he's losing heat. Let's go ahead and finish this side here. The mass of this water, I am going to make my measuring cup filled with 2 cups of cold water, of hot water. 2 cups. It's, you know, I'm using an American measuring cup, so it's not written in liters, it's written in cups. So let's go ahead and do a conversion so we can kind of figure out, we need to figure out the mass, okay? So this is how I did it. If I have 2 cups of water, 2 cups, there are, let's see here, there are 4 cups in 1 quart, and in the back of, or maybe it's in the front, I can't remember, of the textbook, I was able to find the conversion between quarts and liters. 1 liter is equal to 1.05 0.67 quarts. So if we go ahead and put that in our calculator, see, we got to get rid of the American and we got to get into the, let me move this up a little bit, into the SI units, which is for volume, which is liters. There we go. All right, so 2 divided by 4 divided by 1.0567, and that gets us 0.473 liters. So our water sample is 0.473 liters, which we know is equal to 473 mils. Okay, I did that in my head, but that is the same thing. Now, remember, the density of water is approximately, this is a little bit of a stretch, but it's approximately 1 gram per mil. It's different at different temperatures, but we'll just assume that it's 1 gram per mil, which tells me that my water sample is 473 grams. See, with water, you can make these assumptions about, you can convert volume to mass through density. All right, so I'm going to go ahead and do that. That was a lot of explanation to get the mass, but my water sample is 473 grams. Our specific heat capacity is 4.18 joules per gram degree C. And the rest, the T final is what I'm solving for. So I'm just going to leave that alone. I have everything plugged in that I can from this left side of the equation. All right, the right side of the equation. The right side of the equation is going to be a little bit more difficult because what happens to the ice is more involved. All right, so let me erase this here. Clean this up a little bit. All right, let's think about what's happening to the ice. And this is going to be where that heating curve concept is going to be helpful. Let me go ahead and draw, oops, that's going to make this up a little bit. Oh. Okay, close enough. That says heating curve. This is temperature in degrees C. This is heat added. Let's talk about our ice. As soon as that ice gets dropped into that hot water, what is its first phase? What's happening to it? Well, let's talk about what temperature it's at. It's at negative 17.8. Let's just say negative 18 for the graph. Negative 18. Okay, when you are not at like a melting point or a boiling point, in this case, it is below its melting point. It's colder than when it's going to melt. The very first thing that's going to happen is as you add heat, its temperature is going to rise. Even ice is not, it can get warmer and still stay ice. It's actually not going to turn into water until it hits 0 degrees C. So for the first 18 degrees, it is going to just raise its temperature until it reaches 0 degrees C. That's when, that says 0 right there. That's when it's going to begin its phase change. So then, while it's converting from a solid to a liquid, just like the example of the boiling water that I started this video with, it is not going to raise its temperature. During this phase, all of that added heat that's coming, in this case from the hot water, is going to breaking those intermolecular forces that held it into a solid and allowing it to be a liquid. And it's not going to be raising its temperature during this phase. But once all of that's completed, and I think you know that this ice is going to melt. When you put ice into almost boiling water, the ice is going to melt. There's enough heat in there to melt that ice. Once all of it is melted, it is then going to now start on its journey to raising its temperature again to whatever amount of heat is left in that storage to raise it as high as it can to kind of get to that, whatever that final temperature is. So at the end of the day, the ice is undergoing 3 different phases. And this is why this lab is kind of a little bit involved, which is why I'm going to do it with you here. This first phase, remember I told you that any of these diagonal phases are all about Q equals mCs delta T. Okay, that's governed by this law, Q equals mCs delta T. But during this second phase, the phase change, this part of the curve, the amount of heat added is going to be related to, or it's going to equal what's called the delta H of fusion. It's the heat of fusion. It's called. It's a constant for water. It's basically the amount of heat required to melt. I don't know if you remember, fusion and melting are synonymous. Required to melt ice in this case. And it's a constant, and it's a number that we can look up, times the number of moles. And that's going to govern this part of the curve. And then once again, we're at a diagonal part, and once again, it's Q equals MCS delta T. So we're going to have to think about what's going on with the ice, and we're going to have to take it through all three phases. So now let's kind of start getting into that here. So we're now on the right side of the equation. So the amount of heat that's lost by the water is going to have to equal the amount of heat that's picked up from the ice, but from all three phases. So the first phase is this here. Let me just write the word first. This part. It's going to be related to the mass of the ice times the specific heat of the ice times the delta T. Now, the delta T is going to be easy. It's going to be final minus initial. So 0, the final temperature of this phase is 0, because it's going to go from negative 18 to 0. So that's its final temperature, minus, in this case, negative 18. So the delta T for this first phase is 18 degrees C. Okay, so that's that part. Let's go backwards here. What is the specific heat capacity? So right, I'm basically inserting this equation, MCS delta T, in for Q of ice. The specific heat capacity of ice, it's actually a different number than the specific heat capacity for water. It's actually 2.0, I have to look this up, 2.09 joules per gram degree C. Wait, you know what? I'm just realized I'm writing this in the wrong place. Let me write this below. I'm supposed to be doing it here. So I'm going to do math in just a second. The specific heat, 2.09 joules over gram degree C times well, I called it negative 18, but let's be more exact, 17.8. 17.8 degrees C is the delta T for this first phase. Now, the mass of the ice. This is another thing that, you know, because we're at home, we have to just do the best we can. The ice is a rectangle, okay? So knowing density means you can get mass from volume. So I was thinking, well, if I can just figure out the volume of the ice and use the density of the ice, I can figure out its mass. We learned two ways to get volume when we did those cylinders. One was water displacement, but that's not going to work because as soon as we put the ice into the water, it's going to melt and change its volume. So that's not going to work. So I just said, let's just measure it using a ruler, and I did. I don't have it with me right now, but I measured the ice, and it was 4 centimeters times 3 centimeters times 2.5 centimeters, approximately. It was very approximate, but I measured it in centimeters, and so you can get cubic centimeters when you do length times width times height. So if you do 4 times 2.5 times 3, that actually gets you 30 cubic centimeters for a volume. 30 cubic centimeters for a volume. Now I want mass, okay, because you can get mass from density. So if my ice, let me just go ahead and do it over here. I'm kind of running out of room. If my ice is 30 cubic centimeters, I need to know the density of ice. Now, ice and water don't have the same density. That's why ice floats on water, because it's less dense. Okay, that's actually a big deal. Ice is less dense than water. So I had to look that up. I didn't know it by heart. The density of ice is 0.92 grams per cubic centimeter. So this is getting me the mass of the ice, and it turns out to be 27.6 grams. That is the mass of the ice. So I have the last part of this here, 27.6 grams. So essentially, this is my first phase of the ice. This is getting ice to raise its temperature to its melting point. Let's keep on rolling. As soon as it reaches that 0 degrees C, the heat keeps coming in. Now what does the heat go to? Now the heat goes to the second phase of the ice. This is this part of the curve. Now we're trying to melt the ice. And now the heat is equal to the delta H of fusion times the number of moles. And so what I had to do was look up the delta H of fusion of ice. And the delta H of fusion of ice is 6.02 kilojoules per mole. All right, so let me go ahead and put that in there. That's the delta H of fusion, 6.02 kilojoules. Now immediately I can see I'm going to have a joule here, but kilojoules over here. So let me go ahead and make this, let me put it into joules right away. 6.02 kilojoules is 6020 joules per mole. And I have to times that obviously by moles. So you can see the next thing to come is the number of moles. How can I get the number of moles? This is easy. My ice is 27.6 grams. This is just a gram to mole conversion. So you can, most of you should be pretty good at this now. It's just going to be 27.6 grams. I'm running out of room, but it would be times 1 mole over 18.016 grams, or you could think of it as being divided by, but I just always think of it as a conversion factor. If I divide that by 18.016, which is the molar mass, I'm getting 1.53 moles. 1.53 moles. And that is the completion of the second part of my ice. Now, the third. Notice these are all just going to give me nice numbers. This one here is where I'm going to have another T final. So I'm getting closer to answering this question here. I'm just looking at my board here. If I had a bigger board, this wouldn't be too much of a problem, but let me just make this a straight line. I'm just recopying joules over gram degrees C. That is, I just replaced it. That is what our equation looks like left to right. And I've got my third phase coming here. It's involved, I know, but it's involved, but it's also very simple, and it's pretty cool that it actually works. The third phase. The third phase is now taking that ice that now has all melted and become cold water, but now it's still 0 degrees C. Now all the heat is going to be raising the ice's temperature to whatever, that thermal equilibrium temperature, that final temperature is. So now we're at this part of the phase. Once again, now we still have 27.6 grams of water. Now it's water, okay? It used to be ice, now it's water. Now we can use the specific heat capacity of water, 4.18 joules per gram degree C. And now we have its delta T, which is T final, minus T initial. But the initial part of this phase is 0 degrees C. This is the final. The initial part of this phase is 0 degrees C. So this is a 0, which goes right here. Now, believe it or not, I have an equation that I can solve. Let me go ahead and start working this equation out. I've done a lot of kind of side steps here, but let me go ahead and, well, let me leave this guy up for the final answer here. All right, let's see what we can do here. Got a lot of numbers. I'm going to start over here. Let me figure out what these two combined together are. So 473, well, actually negative 473 times 4.18. Let me just get that number first. So that's negative 1977 times T final minus 95. I'm going to have that equal. This can give me all one big number. And by the way, it's going to be joules. So this part of the ice's experience is 1026. And you know what I'm going to do? I'm going to start dropping my units, 1027 actually, because I know that my final temperature is going to be degrees C. 1027. So rather than kind of get too laborious, and I've made all the units match, like he's in joules, all the masses were in grams, so I'm good to go. This one's in moles because the delta H of fusion is per mole. That's why that one works in moles. All right, now to 1027, I'm going to add this number, 6020 times 1.53. And I'm getting 9210, 9211. I know I'm rounding a little bit, but it really won't matter too much. And now the last part here. Let me get this front number, 27.6 times 4.18. That's 115.4 times T final minus 0. I'll just do it minus 0. All right, now I've simplified all the math that I can, but you can see now it's looking pretty good because I only have one unknown, and that's T final. So now let's start working it out. I'm going to have to use the distributive property here, but I'm not afraid. It's going to work out fine. So negative 1977 times T final plus, because it's negative times a negative, but I'm going to do 1977 times 95. 187,815 equals, let me add these two together. 1027 and 9211 is 10,238. And now let me distribute this guy, plus 115.4 T final. Now, I also can distribute this to the 0, but that times 0 is 0, which is just going to give me 0, like basically negative 0. So you can just ignore that part. All right, now we're getting closer to an answer here for T final. Now it's time to combine like terms. Let me go ahead and add 1977 to both sides, 1977 T final to both sides. That way I'll get a positive number for this unit here. So 1977 plus 115.4, 2092.4 T final. And then let me go ahead and move this term over to the other side. Minus 10,238. So I've got 187,815 minus 10,238. And that's good. That's still a positive number, which is good because T final should not be, I wouldn't expect it to be negative. It's not going to go below 0. All right, getting very close to a final answer here. We're trying to get T final. We just need to divide both sides by 20.92.4, and we will get the expected final temperature of our experiment. Let's see. 84.9 degrees C. 84.9 degrees C. Now, let's just make sure I got this. I'm just checking my math. Okay. Now that is my expected temperature if my starting temperature was 95. In just a minute, I'm going to go get this experiment set up, which is going to take me about 2 minutes. So just hang on tight. And I have a thermometer, which can measure, it's like a meat thermometer, but it can measure the sample. And what we're going to do is just see for ourselves what the final temperature turns out to be. Now, I'm not sure I can get it this hot. We'll see. We'll find out in just a little bit. But what I'm going to have you guys do is redo these calculations with the new temperature, okay, of the new water. The ice you can assume is the same. It's from the same ice cube tray, and everything about the ice is the same. So essentially, this entire right side of the equation is all the same. The only thing that is going to change is this starting temperature. So instead of being 95, it's going to be something else. And what I'd like you to do is find out what the expected T final will be for our experiment, and then we'll see how well it matches. So give me about 2 minutes. I'm not going to stop the video because I don't know how to like join it together or whatever, to be back with this little mini experiment, and we'll see what happens. All right, I promised you a very rudimentary experiment, and it is what it is because I'm home and I only have what I have. Just so you see, I tried to make this measuring cup a little bit insulated because I don't want all the heat that I'm trying to go all the way into the ice so I get like an accurate thing. I don't want all of it going into my hand, into the air. It's going to be a pretty big source of error actually, but we'll do our best by making it a little bit insulated. Okay, so I put a little hat on. I've got this wrapped in a paper towel, but you can see, maybe you can see that I poured 2 cups of pretty much almost boiling water. I'm going to put the cap on it and let us get the initial temperature, the number that is going to go in here of the sample. So I'm just going to drive this meat thermometer through here. I'm going to let it rise. You can see it is raising. 62, 64, 66. °C. I have it set on a degree C reading. Okay. You know what? It's going down now, so let's call it 70. So it's not near a 95. We're going to call it 70. And now what I'm going to do, I've got my ice cube. I also wrapped it in paper towel because I didn't want it to melt too much. Once again, probably a source of error. You can see it's not a perfect square rectangle, but I tried, okay? I am dropping it into the hot water, and you will see now it's not stirring or anything. Maybe I'll stir it in a little bit, but you can see that the temperature is falling of the water because the water is losing heat. Let me just narrate what's going on. At first, it's losing heat to the, here, let me go and see if this ice is melted. It's losing heat to raise the temperature of the ice. Let's see if you can see the ice. The ice gone? Woo. No, ice is still in there. I had to take my insulation off, but I am getting, whoops. You coming back? Seems to me like it's settling at 64 degrees C, and my ice is melted, which means we can assume if the temperature has stopped changing and the ice is all melted, we can assume, I just stirred that a little bit, but then again, actually, yeah, when I stirred a little bit, let's call our final temperature 63, okay? 63 degrees C, let's call it that. Our final temperature of the system, and you can see once again, all that ice melted and it reached 63 degrees C. So now we are just about done with this lab. What I want you to do is go back, redo this calculation with what we said was the initial temperature, which now I can't even really quite remember what it was, but I'll go back and look at it in the video, and see if you get 63 degrees C as a final temperature. Now, probably you won't, but see how close that you get. I mean, we should all get the same answer. I'll go ahead and do it myself as well. As a last part of this lab, what I'd like you to do is calculate something called percent error. Percent error is not the same thing as percent yield, and we don't really use it too often in this class, but it's something that this experiment is kind of pretty good works for. I would like you to figure out how much error was in that experiment. There was kind of a lot in terms of reasons. It wasn't that insulated. I used a meat thermometer, okay? The ice wasn't exactly a square, so I probably made some errors over there. When I moved the ice from the freezer to my office, it lost temperature there, or sorry, it gained temperature, it warmed up. So lots of error. But let's see what, it can be calculated how much error we had. And this, you know, if you go online, you can get a bunch of different definition or equations for percent error. I happen to like that percent error is going to equal the absolute value of the observed value. So this is going to be the 63 degrees C minus the, some people call it the expected, some people call it the, what was the other word? The calculated. Whatever one you expected. So this is going to be the result of our T-final calculations divided by, or so value, divided by the expected or calculated value for T-final times 100 because we want it to be a percent error. So say we all just did the experiment. We all are going to get a 63 here. Say you calculate that it was supposed to be, I don't know what it's going to be. I haven't calculated it yet myself. Say you calculated it was supposed to be 68. You would put in a 68 for here and for here, and you would get what's called the percent error. And it shows how much your experiment is off from what like the laws of science declared it should be. And it can give you a sense of how rough your experiment was. I would expect ours to be pretty rough, but it would be interesting if it's close. So I'm curious to see myself. That is the lab. All that I need to do for you guys to receive 10 points for this lab is to show me a photo of your notes. I'd like to see that the proof that you watched the video. And I would like to see your final calculation using the initial initial temperature that we read together on the for the actual experiment that we just did. Just basically recalculate T-final, going through the algebraic steps that I just did, and report your T-final that you expected, and then go ahead and calculate the percent error for our experiment. And hopefully that was clear enough and somewhat interesting. I think it actually gave me a chance to talk about different things that we might not have been able to talk about if we hadn't done it. So that was good. It's kind of fun. Anyways, good luck, and hopefully that was clear enough. Take care.